All right, senior math, we are talking about correlation coefficients today. So you should have just finished activity where you were guessing celebrity age, and you did a Desmos activity that related with that, where it sort of showed you how good you were at guessing age based off a number known as the R value or R factor. Jumping into this, so when we talk about correlation with scatter plots, we have three types of correlation. We have positive correlation, we have negative correlation, and we have no correlation. But oftentimes those correlations can be skewed a little bit. Sometimes we have points that are all very, very close together with their data. Other times we have points that are all spread out with their data. But they may have the same correlation. But we can determine how strong of a type of correlation is using something called correlation coefficient. So correlation coefficient, which is usually represented by the letter R as a variable, like R equals, correlation coefficient helps us determine the strength of correlation, so how closely those points are close together. It can range from anything from a strong positive correlation all the way to a strong negative correlation, and we have weak correlation in the middle and even no correlation. So for example, this number is always going to be a decimal, almost always going to be a decimal. It's going to be ranging between the numbers -1 to +1. We're always going to be between -1 to +1. So for example, if R is -1, this is a strong negative correlation. It's a very, very strong negative correlation. If R is +1, this is going to be a very, very strong positive correlation. I guess flip-flop for you in the video. And if it's 0, there's no correlation. Now, written down here below, this is actually R equals 1. And this is R of -1. It's kind of backwards down here. But this kind of gives you a visual representation of what some of these correlations look like. So when the points are together perfectly, that's a perfect correlation. If it can be perfect positive or perfect negative, depending on which way it's going up or going down. That is going to be your perfect positive correlation or perfect negative correlation. Those are going to be your R equals 1, R equals -1. While a strong correlation is going to be something like R equals 0.9 or R equals like 0.8. 0.9. This is a strong correlation. This means your points are very close together and they're all increasing at that same rate. And it can be strong positive, or we can also have a strong negative. If it's like R equals -0.8 or -0.9, somewhere around in that range, that would be an example of a strong negative correlation. They're both strong because they're both close to the ends of our correlation. So the closer you are to 1 or the closer you are to -1, the stronger you're going to be. It just determines whether 1 or -1 just determines whether you're positive or negative. Weak correlation is going to be something like R equals 3 or 0.3. R equals 0.3 or R equals -0.3. These are examples of weak correlations. The points are going to be more spread out. They're going to be more distant from each other, but they're still going to have that general pattern. They're just going to be more variable in them. And then anything for no correlation is like R equals 0. Right in the middle, you have no correlation. Anything close to 0, like very close to 0, like 0.1 or things like that, those are going to be examples of no correlation. But R equals 0.3, R equals -0.3, those are weak correlation. So looking at these three scatter plots, let's see if we can figure out what type of or which of these has a strong negative correlation. So looking at each of these, which of these have a strong negative? Well, this one has a negative correlation. It seems to be going down, but if we look, our points are pretty spread out. They're pretty all over the place. So this would be an example of a weak. Sorry, I'm writing with my mouse today. So it's a weak negative correlation. This one, it's like barely going anywhere, if up at all. So this could be either no correlation or very weak positive correlation. This one is going up, but it's going up at a pretty tight rate. So this would be, I would say this is a strong positive. And then this last one over here, we're going down and our points are pretty close together. So this would be an example of a strong negative correlation. So this is our example. This is the one we're looking for, a strong negative correlation. We're going down and our points are tightly knit together. They're close together. So how do we find correlation coefficient? How do we find this R value? So on Desmos, we can actually do this. We actually have all the materials to do it. So let's say you're given some data, like this one here, and we graph it on Desmos. So you're given a table, you graph it on Desmos, you type in your y1 squiggle m x1 plus b, that formula we were putting in yesterday. If we look, R is one of those things that's listed below. So we look R value, R equals -0.8. 0.8458. That gives you the correlation coefficient right there. So our correlation coefficient for this value would be R equals 0, negative 0.858. So if I were looking for the correlation, I could just type in R equals negative 0.858, I think is what I said. 8458. I don't know where I was going. And this is an example. So it's a negative value. So I know I have a negative correlation, and it's close to -1. So this is an example of a strong negative correlation. So it's going to be strong negative correlation. So that would be my correlation coefficient. Or this one. So I have this data here, my independent variables and my dependent variables. Plotting this on Delta Math, or sorry, not Delta Math, plotting this on Desmos, I see that I have a correlation coefficient of 0.9987, 0.9987. So if my correlation coefficient R equals 0.9987, well, based off that, that must mean we have a strong positive correlation because we're going up and our points are very close together. And our number, our R value, is very, very close to +1. So this is an example of strong positive. Strong positive. There we go. Last one. So we have this data. If we plotted this into Desmos, we could figure out what type of correlation coefficient we have. If we graph it. Oh, maybe this one isn't on Desmos. Okay, but we can see, okay, if I look, my R value is right here. I have negative 0.44. So if I look, my points are kind of all spread out. And if I have an R value of R equals negative 0.44, this point's pretty close to -3. So I would say this is a negative. It's a negative correlation because I have a negative R value, but it's also, my number is closer towards 0 than it is towards 1. So this is a weak negative correlation. I'm closer towards 0 than I am towards 1. So it's a weak correlation. If I'm closer towards 1 than I am to 0, then it's a strong correlation. But this was an example of a weak correlation. And if I am 0, I'm no correlation. We have one last thing to talk about. That is called causation. So we have something called causation versus correlation. So causation is when a change in one variable causes a change in another variable. It's called causation. So it causes the other variable to change. It causes a difference between the two. Causation produces a strong correlation between the two variables, and the converse is not true. In other words, correlation does not imply causation. So just because there's a strong relationship doesn't necessarily mean they affect each other, but if there is a cause, they will produce a strong correlation. So it's important for us to be able to determine, is something a causation or is something a correlation? Are they related, or are they just have some sort of relationship that seems to be connected, or do they actually affect one another? So which situation does not show causation? So let's try to figure out which of these is causation, which of these is not. So when the student population at a school increases, the number of teachers at the school increases. So having more students at the school causes you to have more teachers, right? In order to teach, most of the time, in order to teach those students, you have to have more teachers. So this is an example of causation. More students causes more teachers. When the amount of sugar in a quart of apple juice is reduced, there are fewer calories in that serving. Calories are based off of amount of sugar in things. So if you have less sugar, you have less calories. So that is causation. They directly impact or directly affect each other. When there are more workers on a project, the project is completed in less time. So does having more workers cause the project to be completed in less time? Most likely it will. Typically it will, but not always. Not every single time having more people working on something is going to get it done less. Eventually, you're probably going to just throwing more people on can actually slow it down. So there's typically a positive relationship between the two, but this does not cause the project to get completed in less time. And then when there is more protein in an athlete's diet, the athlete scores more points in the game. Is that an example of causation or correlation? So this is an example of correlation. Having more protein makes you a better, or gives you more energy, which is probably going to give you a better player. But just feeding someone a bunch of protein doesn't mean that they're going to score all the points of a game. Just protein doesn't cause points. Protein causes energy, which can be fueled into ability, which can help cause points, but it's not going to directly impact. It's not going to directly cause points. It helps, but it doesn't cause it. So which situation best represents causation? Of these, which of these is best causation? So when a number of bus stops increase, the number of car sales decreases. So the number of bus stops increase, the number of cars decrease. Is that causation? Does having less bus stops increase car sales? Not necessarily. Having more bus stops probably makes it less likely that people have to drive as much, so it probably makes less people need to buy cars, but it doesn't cause car sales. So this is not causation. When fewer firefighters report to a house, the damage caused by the fire decreases. Is this causation? When there's fewer firefighters at a house, does that make it less likely that there's going to be fire damage? So fewer firefighters probably means the fire isn't as bad because you don't need as many people there. But fewer firefighters, not sending anyone to a house doesn't mean you're going to decrease the damage. It's not causation. So this is not causation. Having less doesn't necessarily imply there will be less damage. When ice cream sales increase, incidents of sunburn increase. So do ice cream sales cause sunburns? No. You would sound like a lunatic if you thought about that. But they have a correlation. So both of them are going to increase in the summertime because in the summertime, you're probably eating more ice cream and you're probably outside in the sun more, so you're probably going to get more sunburn. But it doesn't cause the effect. And when it rains several inches, the water level of lakes increase. So does rain increase water levels? Yes, that is a direct impact. That is a direct causation. Rain causes water levels to increase. So this is causation, while the rest of those are just correlation. So hopefully that helped explain a little bit of causation versus correlation as well. Let me know if you have any questions over correlation coefficient or causation versus correlation. You're going to have a little bit of practice over this. So let me know if you need any help.